BioFil3D is a 6-person team composed of Amalia, Mathieu, Amina, Fernand, Florian, and Alexandra. We all are last year master's degree students at the Graduate School of Chemistry, Biologie and Physics of Bordeaux, specializing in innovative materials and processes for the industry of the future. For our last year of studies, we had the opportunity to carry out a project in partnership with the Gse, a research laboratory based in La Rochelle, France. Throughout the course of this project, we worked in collaboration with the research lecturer Amer Hamami, PhD candidate Mohamed Sawadougou, and supervised by senior lecturer Marie Duquesne.
Je m'appelle Amer Hamami, je suis enseignant-chercheur à l'Université de La Rochelle, au laboratoire Gse, et je travaille principalement sur la durabilité des matériaux de construction. Et récemment, on a engagé une étude sur l'incorporation des matériaux à changement de phase dans des éléments de paroi.
En fait, je suis doctorant en début de deuxième année au laboratoire des sciences de l'ingénieur à La Rochelle de l'Asie. Et je travaille sur l'incorporation des matériaux à changement de phase dans les enveloppes des bâtiments. C'est des matériaux à changement de phase qui sont d'origine biosourcée, qui ont des températures de fusion dans la gamme du confort thermique entre 15 et 30 degrés. Du coup, le but de l'intégration des matériaux à changement de phase dans les bâtiments, s'inscrit dans un contexte de réchauffement climatique général où on essaie d'optimiser la consommation d'énergie dans les bâtiments. Et les MCP, justement, possèdent une capacité de stockage qui est énorme comparée aux matériaux de construction usuels tels que les briques, les bétons et autres. Et justement, en intégrant ces matériaux de très forte inertie thermique, on arrive à stocker énormément d'énergie et réduire la consommation d'énergie pour le chauffage ou pour la climatisation.
Donc, un des axes que l'on suit, c'est l'incorporation de ces matériaux à changement de phase dans des structures imprimées en 3D, et donc un intérêt particulier à fabriquer des filaments comme vous le faites avec des matériaux imprimables et avec du MCP incorporé dedans.
BioFil3D consists on manufacturing a filament for 3D printing using the Fused Deposition Modeling or FDM process. This technique works by depositing successive layers of polymer or composite material. The material is heated, melted and deposited by a nozzle, guided by a motor, following a path defined by a computer-aided design, also known as CAD file, within the scope of study of the Gse and more precisely for that of Mr. Hamami and Mr. Sawadougou. Our filament is bio-based and has interesting thermal storage properties. As of today, the final application of our filament is to be used in the construction of wall elements for buildings, intended for intra-seasonal storage and during energy consumption peaks. Now, in order to achieve our goals, we have defined the following specifications.
As the main objective is to have a biosource material that is both printable and with good thermal storage properties, meaning higher than 80 Joule per grams, we decided to choose two components which, when combined, meet these three aspects: a polymer matrix coupled with a phase change material or PCM. Before moving forward, let us clarify what a PCM is. As its name suggests it, a phase change material is a component which can undergo a phase change. Its particularity is that, while transitioning, the material can absorb or release thermal energy, storing what we call latent heat or heat of transformation. When sufficient, this energy can provide useful heating or cooling. These materials can therefore improve buildings' energy performance and their residents' comfort. It could also be useful to fulfill new thermal regulations. We count three different types of PCM according to the phase transition they can undergo. First, solid-liquid PCMs, which are the most used due to their high heat of transformation. They can, however, potentially suffer leakage when in liquid form. Secondly, there are liquid gas PCMs, which have even higher heat of transformation than solid-liquid PCMs, but are impractical for thermal storage when in gas form. Finally, solid-solid PCMs, which, while showing relatively low heat of transformation, ward off leakage as there is no liquid state.
Now coming back to the specification, in order for the material to be biosourcé and printable, we decided to use polylactic acid, a widely used polymer for 2D printing. As for the phase change materials, because we want the filament to be used in wall element for building application, we need the PCM to show a transition within the thermal comfort range of temperature in a building, meaning around 20 to 30 degrees Celsius. Therefore, we choose two types of plant-based oils, capric acid and lauric acid, respectively with 10 and 12 carbon atoms. Both of these acids are biosourced and have a high latent heat, respectively 155 and 175 joules per gram. Note also that these two organic PCMs melt respectively at 31.6 degrees Celsius and 43.2 degrees Celsius. Another important point, these PCM are of the solid liquid type. We also choose to produce filament with eutectic mixture of capric and lauric acid, as eutectics possess a melting temperature lower than that of their component. On the side, we choose to produce a sample with palmitic acid as the PCM component, which is an acid with a carbon chain of 16 atoms. This choice was made on the theory that the longer the carbon chain, the higher the heat of transition. The last step of the specification is that we don't want any delay or particular kinetics during the fast transition. Other point, the material should be fit for interseasonal storage. Therefore, the material should be quick to respond and resistant to numerous charge and discharge cycles.
Following the specifications, we first decided to check if our reagents were mixing well. For this, we produced samples of 5 grams with 20, 30 and 40% by weight of PCM. Then, we melted the mixtures on a heating plate with a sand bath at a temperature of 210 degrees. This temperature was chosen as it is slightly higher than the melting temperature of the PLA used in our experiments, a value measured with a Koffler bench. When beginning to melt, the very viscous mixtures were stirred with a spatula. After 20 minutes, the mixtures containing capric and lauric acid seemed fully melted. However, it was not the case for the ones with palmitic acid, as the final mixtures were completely heterogeneous. It can be explained by the fact that the two reagents are immiscible because PLA is hydrophilic, while palmitic acid is very hydrophobic with its 16 carbons chain. Therefore, we decided to remove the palmitic acid as an option for the PCM component. Additionally, we chose to reduce the quantity of PCM inside the samples, as the higher the weight percentage of PCM is, the harder it would have been to obtain a smooth and steady filament.
Following, we decided on producing filament samples using a microconical twin-screw extruder. We first melted the PLA into an oven at 200 degrees Celsius and grinded it to obtain smaller pellets. Then, we weighed the reagents to obtain 5 grams of product with 15% by weight and 20% by weight of PCM. Next, we inserted the reagents into the extruder's hopper and extruded the filament samples between 140 degrees Celsius and 160 degrees Celsius. This range of temperature allowed us to obtain filaments that extruded well and that were not too liquid. With the 3 types of filaments, we observed a noticeable color transition. For samples with lauric acid, the filaments were white at room temperature and became translucent when heated. By naked eye observation, this color transition happened around 40 degrees Celsius, which is in the same range of temperature as the lauric acid melting temperature. For the capric acid and the eutectic samples, the filaments were translucent at room temperature and became white when cold. We came to the first conclusion that these color transitions were a visual proof of the phase transition. In order to verify this hypothesis, we decided on doing differential scanning calorimetry analysis, to which we'll come back later. To go further with our project, we decided to check the printability of the filaments that we produced, a step that we were able to do at the Lassie laboratory. The filaments were placed in a Creality 3D printer working at 200 degrees Celsius with a build plate temperature of 50 degrees Celsius and a printing speed of 20 mm per second. We were happy to see that we could print sample with the filaments. Now, moving on to the characterizations of the materials.
We first chose to verify if the sample were leaking when going through their phase transition. Therefore, using an oven, we established a temperature gradient between 25 and 70 degrees Celsius to represent the outdoor conditions in summer, taking into account a margin of error. The color change observed with the filament confirms that the PCMs undergo their phase change. The use of an absorbent paper allows us to affirm that no leakage takes place with the different samples.
Some samples were observed under environmental scanning electron microscopy. The filaments were cross-cut. We could then compare the inside filament containing capric acid with the pure capric acid and observe the eutectic filament. The images captured showed the same kind of structure between the capric acid filament and the pure acid, proving that the acid is encapsulated in the filament. The composition spectrum revealed the rightful presence of carbon and oxygen atoms as they are present in the acids and PLA alone. Silicon and aluminum impurities were observed in a small quantity and are due to the process. The samples were analyzed by Fourier transform infrared spectroscopy in order to study their chemical structure. We could compare the absorption spectrum of the filaments with the one for the printed sample for the different acids. The overlay of the spectra shows that the printing step did not denature the material and thus has the same properties after printing. Then, we verified if some chemical reactions happened between the PLA matrix and the acids, which could have impacted the filament's chemical structure. We compared the PLA and capric acid spectrum in blue and green with the filament in red. We observed an important decrease of the peak intensity around 2,900 cm to the -1 for the filament, corresponding to the disappearance of CH alkane bonds. On the other hand, around 1,200 cm to the -1, a peak appeared for the filament, corresponding to the formation of CO bonds, typical of the ester function. Therefore, it is legitimate to think that a reaction of transesterification happened between the PLA and the acids during the extrusion. Future studies should include further investigation of the material's chemical structure.
Finally, thermal behavior of the extruded filaments was studied by differential scanning calorimetry, or DSC, and by thermogravimetric analysis, or TGA. The TGA curves show that there is no significant weight loss in the PCM's temperature range of use, that is to say between 15 and 50 degrees Celsius. Indeed, weight loss happens only from 150 degrees and up. By comparison with the PLA curve, the polymer is degrading from 300 degrees. We conclude that the weight loss between 150 and 300 degrees is due to the degradation of the PCMs. The results show a loss of 3.5 mg on average. As the extrusions happen between 140 and 160 degrees, we thus know that our filaments still contain a fair amount of PCMs.
For the Gse analysis, samples were placed in aluminum crucibles and heated on average from -10 degrees to 200 degrees for the filaments at a speed of 10 degrees per minute. Results show the following. For every filament, we could isolate the behavior of the PLA matrix from the behavior of the acids. Indeed, the DSC curves show a crystallization peak around 80 degrees, typical of a polymer that has undergone quenching. Then, a double fusion peak is present around 145 degrees, classic of a polymer that melts in a quite large temperature range, due to the presence of several nucleation sites or spherulites. The part of the curve corresponding to the PCM behavior is situated in between under 60 degrees. For each filament, we observe a crystallization peak followed by a fusion peak. For samples with capric acid, the fusion peak is around 33 degrees and the crystallization starts around 10 degrees. The corresponding latent heat is of 21 joules per gram. For the sample with lauric acid, the fusion peak is around 46 degrees and the crystallization starts around 25 degrees. the corresponding latent heat is, on average, of 13 joules per grams. Finally, for the sample with the eutectic, the fusion peak is around 25 degrees and the crystallization starts around 11 degrees. The corresponding latent heat is of 16 joules per grams. These values attest to the storage capacity of our products with visually no supercooling. Considering our specifications, that is to say, a biosourced material that is printable and with good thermal storage properties, a PCM that shows a transition within the thermal comfort range in a building around 20 to 30 degrees, and a material that shows no delay or particular kinetics during the phase transition, fit for intra-seasonal storage. Our three filaments are in line with these requirements. However, the samples with capric acid and with the eutectic show better results in terms of thermal storage properties. Additionally, the transition temperatures are the closest match to what we were expecting. Consequently, our recommendations for future studies are to select samples with capric acid and the eutectic.
What about the future of BioFil3D? The Gse analysis that we executed showed latent heat values lower than the 80 joules per gram expected in our specifications. It would thus be interesting to further study ways of increasing these values, consequently improving the thermal capacity storage of our products. In addition, the no supercooling property should be further verified to be sure our materials are fit for intra-seasonal storage. Furthermore, another polymer matrix could be used, which is polyethylene glycol, or PEG. The opportunity to manufacture PEG matrix filaments could in fact be taken, as it meets the specifications. It could then be interesting to make a comparison between the two polymer matrices, PEG and PLA. Additionally, introducing fibers within the filament could be considered in order to reinforce it mechanically. Finally, it would be instructive to study the cyclical behavior of our filaments, that is to say, evaluate the capacity to store and release thermal energy throughout their lifetime.